It really does.
Okay. All right, we are live on YouTube.
Woo! All right,
Yeah.
here we go. This one time, season 2.
We're on season
Yeah,
2?
this is season 2 now, officially.
I'm on
Episode
the
2.
pilot? Oh, okay.
Yeah, episode 2.
All
Sorry,
right.
you missed the pilot.
All right.
Yeah. Welcome back, listeners, viewers, fellow robot hardware nerds. My name is Andrew Gillies, CTO at Urban Machine, and joined today by Jorie and Alex. Yeah, fellow co-founder.
Thank you for having me.
Yes, of course. Yeah. And maybe just a quick, at this one time, what we like to do is talk about how freaking hardware it is, and sort of building in public on our own journey here at Urban Machine, where we're building robots and automation systems to reclaim, recycle waste lumber in the construction and demolition industry, help sort of boot up a circular economy for our built environment. Yeah, and really, by building in public like this, what we're hoping to do is like share our stories, give a little peek behind the curtain, and maybe folks out there might be having similar challenges. Maybe they can get to their goals a little bit faster too. So it's really all about getting down the field a little bit faster. Yeah, and so on the episode today, we're talking about robot calibration. Jory, did we have a snazzy title for the? I don't think we closed the loop there. Do we have a snazzy title today?
I mean, what do you think?
Of course.
It's calibrate and elevate.
Oh, that's so good.
Thank you. Yeah, because that's what you guys do. You guys are, when I was in the warehouse in December, I know the demo robot was not calibrated. Alex hopped in, and then, it elevated the situation. I was able to show off the demo robot because of his.
I think we fixed it a few days later, but you know what?
Yeah, it was. Yeah, it was still better than it was. So.
Yeah. Maybe it's actually a good entryway into talking about calibration, because that's the thing that's interesting when we talk about calibration at Urban Machine. What we ultimately care about is we're using an AI and computer vision system to detect and pick nails out of waste lumber, right? So we have this end effector, we call it a big bird. It's sort of this vicious looking talon that we go, and we want to really precisely go over a nail head, grab onto it and remove it, right? So when we talk about calibration, what we're talking about is understanding from where we think the nail is, and then directing the robot to that position in the physical world, and making sure those two things superimpose. There's no error between those two things, right?
Exactly.
And calibration ends up becoming somewhat a lightning rod for the entire system, because if you're suddenly missing nails, like if there's really anything wrong in the system at all, calibration is going to reveal that, right? And the demo bird is a good example of this. Yeah, but maybe we can.
My commentary on demo bird is, so that's demo bird is our vending machine size nail picker we use for demos. You might have guessed, and basically you put a little piece of wood in, and it picks the nails. And it's not really meant for production. It's more just to show off, like, here's the core tech. And what was happening is it was picking nails, but it was off on one axis. Like, it was picking next to the nail every time. And what calibration revealed is, like, we'd calibrate it and then it would fix itself and then immediately start picking them correctly. And the root cause after investigation was that one of the axes had like a screw that wasn't quite set all the way, a set screw. And so when the axis was moving, it would start slipping. And this kind of gets into like the core intro of like, what is calibration? If your axis is slipping, then you're losing understanding of where you truly are in space versus where you think you are. And that really is what calibration is. It's like being correct about where you think you are and where you actually are in the real world. And this kind of comes back to the digital twin, which is, having a correct understanding of the position of every part of your robot, or the relevant parts of your robot in a digital simulation, so that you can plan movements and say, hey, I want to go from point A in this frame of reference to point B in this frame of reference. And you want to make sure those frames of reference are correct. that your understanding of those frames of reference are correct relative to each other. So what's happening in DemoBird is we were calibrating and it was correct, and then would move and the axis would slip, and then the real world robot was not in the spot that the simulated robot thought it was.
Okay.
Yeah.
And how do you go about finding the right balance?
Yeah, like how do you know where you are? And this is the story.
How do you know where you are?
This is really where the meat of the story is. Like, how do you know where you are? As humans, you don't have to really think about this too much because we have kind of our own built-in sensor stack that sort of solves this problem. I think proprioception is what's like. You can close your eyes.
Like I can close my eyes and then. That was actually hard to do. And that's my finger, right? Because I have an understanding of all the joints, like 60 DOFs.
Yeah.
Yeah, that's actually kind of interesting.
Yeah, that is. Yeah, so as a human, when you close your eyes, you can get a sense of like where, like how bent your elbow is without looking at it, right? It's because each of your muscles and your joints have sort of built-in sensors telling your brain that like, okay, my elbow's at 90 degrees, it's at 45 degrees. Yeah. We need to build that same sense into the robot. That's kind of one of the first steps of it, right? Is like any motor that's moving an axis around in this system, which are like referred to as a degree of freedom, needs a sensor associated with it saying like, hey, this is where I think you are, right? That's really just the core. There's like a whole chain of things that have to come together in order for you to say like, I see something here and now I can direct the robot to here.
Yeah, and I mean, we should probably jump into that aspect, right? It's like, where do you care about being correct? Like what are the frames of reference that need to be correct relative to each other, right? So in the example you're talking about, where you have a camera and it sees a thing, you're talking about a frame of reference relative to the camera, right? You see the nail, you see its XYZ position, but it's in this camera space, right? And so this is a really common problem in robotics is, well, we know where it is in the camera space, but now we want to move it to like the robot's frame of reference so that we can move to somewhere there. And even that isn't really specific enough because robots have a lot of frames of reference. They have, there's like the base of the robot, and then there's like the tooltip that's going to actuate and move onto things, and there's all the joints along the way. And this is usually represented, at least in the ROS world, by something called a URDF, which is we've done an episode on this. If you haven't watched it, you should watch it. It's a universal robot description file, and we have a little representation of this over here somewhere.
That would be a good time to share that. So let's jump over here. I have a few images to kind of help us along. Let's see. Let's start with this.
Yeah. So Andrew and Andrew's team will provide these nice 3D models for the software implementation crew. And what we get usually is these like nice little STLs that provide some nice visuals, but they also provide these frames of reference. Those are those little green, blue, and red rods there. And each of those that has a name it's called a TF frame, so a transformed frame. But we don't have to get into that. The point is that they hold, it's sort of like a point of reference of like, hey, this is like, for example, a nail is, this XYZ relative to the camera, but what is the nail's XYZ relative to the robot that can actually grab it?
Yeah, so we end up with this layer, and probably most folks that would be interested in this are at least somewhat familiar with the idea of a Cartesian coordinate system, right? Where you have like an X, Y, and a Z axis, and there's an origin for those so that you can kind of place things within that coordinate system. So all this is representing are multiple coordinate systems and their relationship to each other in 3D space. So that's sort of this tree, this representation that we're talking about. And each of those coordinate systems we refer to as it's a frame, really, in this whole thing. Yeah. So when you have your physical robot here, right? You can see kind of the parts of the system. This is kind of stripped down a little bit, but at least you can see there's like gantries and rollers and these other geometries that we want to track. And then we have we come up with somewhat arbitrary coordinate frames that track each of these independent moving components. And that builds this tree, which looks like this. So this is the 3D information stripped out. So all you're looking at here are the various coordinate frames, which are those little like green, blue, red arrows, XYZ axes. The rods. And then the yellow, you can kind of see there's arrows that represent the transforms from the relationships from one coordinate system to the next.
So for example, like if I had a URDF of my face, I would probably have like a frame of reference on my left eye and a frame of reference on my right eye and maybe one on my nose, and the like left and the right would be connected to the nose by like, it's like, oh, to get to the right eye from the nose, you'd go up 2 centimeters and right 2 centimeters, for example.
A roadmap, if you will.
Yeah.
Yeah.
And this ties really closely into calibration, because if you know the positions of these things relative to each other and you're correct about it, then you can do nice things like transforming a coordinate from one perspective to another. And that gets you most of the way there to like move a robot to a certain position, for example. And so we actually have a DF frame up there called base camera upper fixed. And that really does represent like, this is where the camera goes in the robot. And this is a robot that we're assembling right now. And so the calibration for this is going to focus a lot on making sure that we know where that camera really is relative to those X and Y joints. This robot can move around in this kind of planar fashion, sort of like a laser cutter, for example.
Okay.
So Andrew's prepping.
I'm getting really bold here and attempting to show this in 3D.
Oh,
Let's see.
I'm
We're loading.
wearing the shirt for the boldness, so
We might as well get bold. Let's
go
see
big
if we.
or go home.
Yeah. Let's see if this works. I might need to.
Does that look good?
Can you see this rotating around?
Oh, now I can see it rotating.
Yeah. So now you can get an idea, right? So we have like some sort of end effector here and some sort of camera frame, and you can see the relationships in all these. So this is of course a virtual representation of the whole thing, right? And I can move some of these around so you can see this.
So yeah, this is actually really cool. So what Andrew's doing right now is he's moving joints around, like kind of like we can bend our elbows. Our robot has various different motors and actuators that it can move around, and he's showing how these different things can be moved around. And this is like the software team, we can make use of this quite directly by saying, well, we want to move the end effector of a robot to a nail position. How much do we need to move these transforms, these frames of reference on the X and the Y position to get there? And then once we know that, we can actually tell them to move, and the robot should end up in front of the nail.
Got it. Okay.
The challenge is that this is a virtual representation.
Yeah.
In the real world, it doesn't match this exactly. There's error, right? And that's where the party really starts.
Yeah. So in a perfect world, you would just like copy paste from your CAD into reality, and everything would be correct down to the thousandth of an inch. But in the real world, when you're assembling, you find that there's like a missing hole somewhere, and you need to drill something, and now everything's offset by 1 millimeter. And oh, we actually need a few washers here that we didn't account for, so we'll put those in there. And
Yeah.
the end effector doesn't reach as far as we thought it would, so we're going to add a few spacers and move everything a few centimeters. Yeah. So,
Or this element is like heavy and droops a little bit under gravity because there's a little bit of elasticity in the robot arm, so you get a little bit of drooping like this. So suddenly you thought you were up here, but the arm bends like a diving board a little bit, and you have some offset there.
yeah.
Right, so that's kind of like, and there's a lot more that mechanically can throw you off there, but that's kind of a taste of some of the things that can happen on the mechanical side.
Sure.
And that's sort of the tip of the iceberg, right? You can also tell a joint to move to a certain position and you tell it, I want you to move forward by half a meter, but it actually moves forward half a meter plus a few millimeters, right?
So is there someone on the mechanical end always as you're doing these, or calibrations?
Well, there's sort of two ways to go about
watch.
it. You could try to make sure that every single part of your robot is two-spec. And that might work for, I don't know, a really big company that has a lot of resources and is deploying thousands of these and can adjust things. But I don't think that's probably not how people do it usually.
It's nearly impossible.
It's almost nearly impossible. So what you end up doing, and what we're doing, is we cut our losses somewhere and decide, well, where do we actually care about being precise, and where do we not care about it? I don't actually care if like the entire frame of the robot is left by 3 centimeters. I just care that I know that the entire thing shifted, so I can correct for it when I'm picking a fastener, for example. So, or like, you know, we want to experiment, and what if we swap the lens on a camera, and now it goes from this field of view to that field of view, and maybe the lens has like a certain tilt, so now the entire frame of reference of the camera is rotated a little bit.
Sure.
Those things can happen, right? So this all comes down to these like calibration procedures, which is some kind of procedure you design for your specific use case to account for the kind of errors that you care about, as opposed to the kind of errors that you don't care about. Like, for example, like, for example, we have wood in our system that moves all the way to a metal detector, and we just care that the metal detector's position is known within like 5 to 10 centimeters. It doesn't really matter, as long as when the metal detector beeps, we know which plank of wood it was on. So a plank is like 6 feet long, so you have a lot of margin there. And at that point, you can kind of eyeball it. But when you're picking a nail, like that's a few millimeters thick, so you actually care a lot about the position of the nail relative to, you know, the end effector and the camera.
Absolutely, yeah. The margin error.
So we've done this a few ways in the past. We have a little picture of kind of one of the ways we went about it.
So here's our first attempt, which is, again, if you've been in the robotics world for any amount of time, one of these probably looks pretty familiar to you.
You might be saying April tag. It's actually an Aruko tag, but we've done both. But this is actually not how we started. We used to calibrate by hand, where we would literally like move the robot on top of a nail and then look at a point cloud from a camera and see like that the robot was off by a few millimeters, and then we would move the virtual representation of the robot to match the real world representation of the robot. And that got us pretty far, but it was very time intensive, and I was the only one that knew how to do it. So we decided to automate that process. And so that process is all about finding the relationship between the end effector of the robot and the position of the camera. And we actually have multiple cameras in our system, so we kind of scope that down. It's like, we actually don't care about the position of the end effector relative to every camera. We care about it from the perspective of the camera that's going to be giving it information about nails. And we only care that the end effector is correct to the other cameras roughly enough so that we can do collision prevention. So you can kind of see how the requirements, the constraints of your system drive and the requirements of your system drive how much accuracy you need and what kind of calibration procedure you end up coming up with. I'd imagine if you were designing generic 6-axis robot arms, your requirements are driven by thousands of customers. So really, you just have to be accurate in every possible way. But for us, we need accuracy between certain points of reference, less accuracy between others. And so we designed for that so we can save resources.
Yeah. So in this case, we're more or less directly inferring what the position of this beak is with this tag. So this tag allows, the geometry of this tag allows the camera to say fairly precisely that the frame of the beak is this. So it literally just looks at that tag, looks at properties of the geometry, like little squares in the border of that, and says, okay, it's like skewed this much, it's this far from the camera, it's this size. That means that the frame of reference for that tag is this. And we know that there's a rigid offset between that tag and the beak because it's just one single assembly. So we can say that offset is fixed. We know where the tag is from 3D space. based directly from the camera. So we know that direct relationship. We can draw a line effectively straight from the camera to that tag, and then measure the error in the URDF that we were showing earlier in that TF tree, and just apply a correction there. And say like, no, you're not where you thought you were, you're here because we see the tag here. And that's it. It's just like a hard offset.
That's super cool, especially because obviously when you're on a job site, you're not there. You the engineers are not there. So
yeah, you're really it behooves you to find a way to do this in an automated manner. Yeah, you can't. There can be no artisanal calibration in the field. Yeah,
we did used to call it artisanal calibration.
Yeah. But even this really only got us so far. Maybe you can talk about some of the problems with this approach.
So if you haven't noticed, the tag is not on the beak. Like Andrew said, we assume that the position of the tag and to the tip of the beak is known. But that's actually not knowable. The beak is a changing artifact. It wears down over time. Like parts of that assembly do actually bend. The April tag, the Aruco tag, can be bent a little bit as well by nails or by just whatever the accuracy of Oshkott's bending process is.
Yeah.
And so even from the very beginning of installing these tags, we had to have two calibration procedures. One to calibrate the position of the tag relative to the beak, which was done, so to speak, artisanally. So I was looking at point clouds and correcting things. And then the other that's automated. And so the automated one could only ever be as accurate as the artisanal one. And if the tag ever started moving or shifting or anything changed there,
a piece of wood smashed into it.
A piece of wood smashes into it and bends things 2 degrees that way, then everything is shot by that many millimeters, and that can affect things. And it's really hard to tell. And it was mostly just the fact that it was so hard to tell why things were failing that we went and took the jump to developing yet another calibration procedure. And so this is the one we're running with right now in production. And we got rid of the tags. There's no more tags. And now we look for the actual shape of the beak. We look for the beak in space and try to calibrate to the point on the beak that would be grabbing nails. And that has worked pretty well.
That's so cool.
Because that's the point we care about. Yeah. That's the point we want to move onto a nail. So I don't care.
All the middlemen. Yeah. Just look right at the beak.
Look for the beak, and if you can find the beak in 20 or 30 locations, so we take pictures, we look at the beak, we try to find it, then we rotate the robot 180 degrees, we take another picture, we try to find the beak. And that rotation is important too, because we found that sometimes mechanically the robot doesn't rotate around a perfect point because it sort of orbits around it. And we wanted to account for that at least a little bit.
And that looks something like this.
This is a video of the robot doing calibration. It takes about 10 minutes per robot on a good day, so about 40 minutes. And usually what we have the operators do is they'll just click calibrate and leave the job site at the end of the day. And the robot will shut off and save power once it finishes. You can see the top robot gantry there moving around to a bunch of different locations, and each time it moves to a location, it's taking pictures and trying to find the beak. And once it finishes, it starts the bottom up.
That's super cool. Now, I'm not trying to be funny. The fact that you honed in specifically on the beak, that aha moment that this is what needed to be. What was that? I mean, it seems so obvious to you now, like that is the point.
I mean, it was kind of like very early on we knew we needed to calibrate to the beak, but it just seemed really hard. It seemed like a lot of resources, yeah. And this kind of in computer vision, when you want to do some localization in 3D, your mind usually jumps to, I should put a tag on it.
Because that whole April tag, Aruco tag stack is open source and really easy to implement. Like there's really well established pathways to get that up and running on your system really quickly with writing very little code around it.
And the real pressure that this is such a startup thing. It was great for this one time. The real pressure came on when we were going to deploy in October, and I had a trip to Japan in October during the same time when the robot would be deployed. And I decided that like the biggest risk we had was calibration not being very good, and because that was part of the stack that I owned so much of, I needed to redesign it. And so I think the week leading up to me dipping out for a while, I built that entire beak calibration. Just cranked really hard in the mornings because there was also this calibration is really hard to develop on because it requires a lot of time spent with the robot. And we were also trying to spend a lot of time using the robot to run wood in the shop so we could find issues before we sent it out to the field. So yeah, a lot of early mornings trying to figure out, hey, how do I detect this beak accurately? But I think when we deployed it, it ended up working. Yeah, there were some kind of funny artifacts of designing a new calibration procedure for a robot that was not designed for that type of calibration. Okay. So one of those things is you might notice like, well, in order to see the beak, the camera must be able to see the beak. And the camera cannot see the beak on all of the birds in all positions. Like, for example, on the side birds, there's a lot of positions where the beak is blocked off by other parts of the robot. You just can't see it. And so a lot of the logic had to do with finding locations where the beak can be seen and then trying to reuse those for future calibration sessions. Also, this relies on the camera being able to see 3D points on a very small surface. And we discovered that for the left bird, the left robot gantry, it like something about the angle of the camera to that beak, just it wasn't quite able to see the beak in enough positions to finish calibration. And so part of our operating procedure was to put chalk, liquid chalk on the beak to paint the beak before you run calibration. And that matte chalk gave the structured light camera like a little bit more surface or a reflective surface to be able to see patterns and get 3D points on.
Yeah.
And so now our operators are trained, they're artisanal painters. They know to go to the left beak and paint it, before at the end of every day.
Okay. So at the end of every day, it has time to dry for the next morning's plug and chug.
They paint the beak and they leave, run calibration. Yeah.
That's awesome. That's really, really cool. I love it. So it's prepped and ready for the next day. Brilliant.
Yeah, and then also all this goes into the next iteration where you can say, okay, now we've honed in on a much more effective method, and we can start designing it from the mechanical side, like clearer features, more robust ways to do this, and make the whole system that much better.
And the next one will be like where it can dip itself in the paint. Like put on its makeup before it goes to bed.
Yeah.
It's night cream.
Yeah.
I love it. You guys, this is awesome. It's really cool. I love this show because I learn a lot about what you guys are doing and your brilliant minds. And thank you for all the analogies to make me be able to understand it.
Yeah, this one you guys move me real quick on. Sure. It's full stack here. Yeah. That's great.
I love it. We also have, we have some job openings for folks who want to work with your brilliant minds.
That's right. Yeah, we have a handful of openings right now. We're looking for a mechanical engineering intern to join us for the summer, and we're looking for a field engineer to help sort of run operations in the field day to day with the robot, keep operations running smoothly, make sure the robot's running smoothly. So those are both open, and you can find both of those. Should be on link through our website.
Yep, on the careers page. Mm-hmm.
Yep, on the careers page, and also on LinkedIn and WellFound.
That's right. Yeah, and our website is urbanmachine.build. So we have a big a little facelift for our website that is going to launch tomorrow. So people can...
tomorrow, really? Wow, okay.
I know, I'm so excited.
On Google.
Yeah.
It feels like, so sometimes you're like pushing this boulder uphill, and okay, it's finally at the top, and we'll release it tomorrow, and then some cool new videos on there.
Any documentaries by chance?
Ooh, yeah.
Be a documentary. Oh, and tonight we do have the documentary. Big reveal tonight at the GFDA event that's going to be at our warehouse tonight. You can still get tickets for that if you're in the Bay Area.
What is GFDA for me and the other viewers?
I'm sorry?
What does GFDA stand for?
Oh, the Good Future Design Alliance. So it's a bunch of people who are into sustainable designing, and part of the reason that they have decided to host in our space is to help those designers and architects get inspired by reclaimed wood, and talk hopefully with Ashley about buying some reclaimed wood for their designs.
Look forward to it.
Yeah. You guys have fun tonight. I wish I was going to be there.
Yeah, too bad, Jorie. Next time.
Next time. It was fun. It was fun being behind the scenes. So I like that stuff. All right. Well, everybody, thank you for joining us today. Sorry LinkedIn didn't work out again. We'll figure this out. I don't know what's happening, but we'll make it happen.
Cool.